Hello, my dear, and welcome to our astronomy course. Okay, today we are continuing study the death of stars. You know, gravity is patient, and so patient it can kill stars. Stars generate tremendous energy resisting their own gravity, but no star has an infinite supply of fuel for its nuclear reaction. When the fuel runs out, the star dies. And all over the sky, astronomers find beautiful nebulae that were puffed gently into space by during stars. In addition, astronomers occasionally see a new star appear in the sky, grow brighter, then fade away after a few weeks or a year. You will discover that what looks like a new star in the sky is either a nova, the eruption of a very old dying star, or a supernova, the violent explosive death of an aging star. Modern astronomers find a few nova. Nova it's worth the same plural of nova. Okay, so astronomers find a few nova each year in average, but supernova are so rare that there are only one or even two each century in our galaxy. Astronomers know that stars die because they occasionally see supernova flare in other galaxies, and because telescopes reveal the remains of stars that have already died, as you can see in this slide. The mass of a star is a critical in determining its fate. Massive stars can die in violent supernova explosions, but lower mass stars die quite dead. To follow the evolution of stars to their graves, you can start by following the life story of a sunspot, medium mass star, as it becomes a giant star. Okay? Then you can see how stars of different masses end their lives. A main sequence star generates its energy by nuclear fusion reactions that combine hydrogen to make helium. It's like in our next topic of today's lecture. Okay? Giant star. So, the period during which the star fuses hydrogen lasts a long time, and the star remains on the main sequence for 90% of its total existence as an energy-generating star. When the hydrogen is exhausted, however, the star begins to evolve rapidly. The nuclear reaction in a main sequence star's core fuse hydrogen to produce helium. I hope you remember this from our previous lecture, right? Okay, because the core is cooler than 100 billion Kelvin, and the helium cannot fuse in nuclear reaction. So it can accumulate at the star center like ashes in a fireplace. And initially, this helium ash has a little effect on the star. But as hydrogen is exhausted and the stellar core becomes almost pure helium, the star loses the ability to generate the nuclear energy that opposes gravity. As soon as the energy generation starts to die down, gravity begins to make the core contract. Also, the core of helium ash cannot generate nuclear energy. It does grow hotter as it contracts because it is converting gravitational energy into thermal energy. See our previous lecture. Okay? So the rise in temperature heats the unprocessed hydrogen just outside the core, and hydrogen that was never before hot enough to fuse. Soon, hydrogen fusion begins in a spherical layer or shell around the exhausted core of the star. Like a grass fire burning outward from the exhausted campfire, the hydrogen fusion shell creeps outward, leaving helium ash behind and increasing the mass of the helium core. The flood of energy produced by the hydrogen fusion shell pushes toward the surface, hitting the outer layers of the star and forcing them to expand dramatically, as you can see on this slide. Stars like the sun become giant stars of 10 and even 100 solar radii. And the most massive stars become supergiants, some thousands times larger than the sun. This explains the large diameters and low densities of the giant and the supergiant stars. In lecture number 8, you learned about the large sizes and low densities of giant and supergiant stars. Now you understand that these stars were once normal main sequence stars that expanded when hydrogen shell fusion began. The expansion of its envelope dramatically changes a star's location in HR diagram. Just as contraction hits a star, expansion cools. As the outer layers of gas expand, energy is absorbed in lifting and expanding the gas. The loss of that energy lowers the temperature of the gas. Consequently, the point that represents the star in the HR diagram moves to the right relatively quickly, in less than a million years for a star of 5 solar masses. A massive star moves to the right across the top of the HR diagram and becomes a supergiant like is here the sun at the top. Okay? While a medium mass star like the sun becomes a red giant, becomes to this. As the radius of the giant star continues to increase, its enlarging surface area makes the star more luminous, moving its point upward in the HR diagram. Giant, supergiant, and like Betelgeuse and the night. Favorite star Aldebaran, the glowing red eye of Taurus the Pole, is such a red giant, so you can see here in this part. With a diameter 25 times that of the sun, but a much cooler surface temperature. Also, the hydrogen fusion shell can force the envelope of the star to expand. It cannot stop the contraction of the helium core because the core is not hot enough to fuse helium, and gravity squeezes it tighter and it becomes very smooth. If you were to represent the helium core of a giant star with a baseball, the outer envelope of the star would be about the size of the baseball stadium. Imagine the baseball size, core, and the star itself, like at the baseball stadium, so gigantic size. And yet, the core would contain about 12% of the star's mass in this small part. When gas is compressed to such extreme density, it begins to behave in astonishing ways that can affect the evolution of a star. To continue the story of stellar evolution, you must consider the behavior of gas at extremely high densities. And normally, the pressure in a gas depends on its temperature. The hotter a gas is, the faster its particles move, and the more pressure it exerts. The gas inside a star is ionized. So there are two kinds of particles, atomic nuclear and free electrons. Okay? Nice. Under normal conditions, the gas in a star follows the same pressure and temperature laws as other gases. But if the gas is compressed to very high densities, as in the core of a giant star, two laws of quantum mechanics come into play. And the difference between electrons and nuclear becomes important. And first, quantum mechanics says that the moving electrons confined in the star's core and can have only certain amounts of energy, just as the electron in an atom, it cannot occupy only certain energy level. You can think of these permitted energies as the rungs of a ladder. Imagine only one. An electron can occupy any rung, but not the spaces between them. Are you agree with me? Only any rung of the ladder itself. The second quantum mechanical law, sometimes called the Pauli exclusion principle, says that two identical electrons cannot occupy the same energy level because electrons spin in one direction or the other, opposite mate. Two electrons can occupy a single energy level if they spin in opposite direction. That level is then completely filled, and the third electron cannot enter because whichever way it spins, it will be identical to one or the other of the two electrons already in the level. Is it okay? Now, a low density gas has few electrons per cubic centimeter. So there are plenty of energy levels available. Let's look at this figure, please. If a gas becomes very tense, however, nearly all of the energy levels are occupied. In such a gas, a moving electron cannot slow down. Slowing down would decrease its energy, and there are no open energy levels for it to drop down to. It can speed up only if it can absorb enough energy to leap to the top of the energy level, where there are empty energy levels. When a gas is so dense that the electrons are not free to change their energy, and astronomers call it degenerate matter. Also, it is a gas. It has two peculiar properties that can affect the star. And first, the generate gas resists compression. To compress the gas, you must push against the moving electron. And changing their motion means changing their energy. And that requires tremendous effort because you must boost them to the top of the energy ladder. And that is why they generate matter, though still a gas, is harder to compress than the darkest hardness steel. And second, the pressure of generate gas does not depend on temperature. To see why? Note that the pressure depends on the speed of the electron, which cannot be changed without tremendous effort. So, the temperature, however, depends on the motion of all the particles in the gas, both electron and nuclei. If you add heat to the gas, most of their energy goes to speed up the motions of the nuclei, which move slowly and don't contribute much to the pressure. Only a few electrons can absorb enough energy to reach the empty energy level at the top of the energy ladder. And that means that changing the temperature of the gas has almost no effort on the pressure. And eventually, many stars collapse into the white dwarf. And you will discover that these tiny stars are made of degenerate matter. But long before that, the course of many giant stars becomes so dense that they are degenerate, a situation that can produce a cosmic bomb. Hydrogen fusion in main sequence stars leaves behind helium ash, which cannot fuse because the temperature, as you remember, is too low. Helium nuclei have a positive change twice that of a proton. So to overcome the repulsion between nuclei, they must collide at a high velocity. But the temperature in the core isn't high enough to produce this collision. As a giant star fuses hydrogen in an expanding shell, its inner core of the helium contracts and grows hotter. When the temperature of the core finally reaches 100 million Kelvin, it begins to fuse helium nuclei and to make carbon. How a star begins helium fusion depends on its mass. Stars more massive than about 3 solar masses contract rapidly, and their helium-rich cores heat up, and helium fusion begins gradually. But less massive stars evolve more slowly, and their core contract so much that the gas becomes degenerate. On Earth, a teaspoon of gas would weigh more than an automobile. And this is for example. In this degenerate matter, the pressure does not depend on the temperature. And that means the pressure temperature thermostat does not regulate energy production. When the temperature becomes hot enough, helium fusion begins to make energy. And the temperature rises, but pressure does not increase because the gas, as you remember, is degenerate. The high temperature increases the helium fusion even further, and the result is a runaway explosion called the helium flash, in which, for a few minutes, the core of a star can generate more energy per second, and then does an entire galaxy. Also, the helium flash is sudden and powerful, and it does not destroy the star. In fact, if you were observing a giant star as it experienced the helium flash, you would probably see no outward evidence of the eruption. The helium core is quite small. Let's look to this slide, please. And all the energy of the explosion is absorbed by the distended envelope. In addition, the helium flash is a very short-lived event in the life of a star. In a matter of minutes to hours, the core of the star becomes so hot that a significant number of electrons get boosted to empty energy levels at the top of the energy ladder. And that increases the pressure and the degenerate condition. And the pressure temperature thermostat brings the helium fusion under control. From that point on, the star proceeds to fuse helium steadily in its core. And that's very nice. There are two reasons why you should know about the helium flash. And first of all, it is so violent and so sudden. It makes it difficult to compute models of stars and be sure how they evolve. Astronomers have to exercise ingenuity to get past the helium flash and follow the further evolution of stars. And second, the helium flash is a good illustration of how science reveals a hidden universe. Astronomers would never have known about the helium flash were it not for the theoretical calculation of stellar models. The Sun will experience a helium flash in a few billion years, but stars less massive than about 40% solar mass never get hot enough to ignite helium. Stars more massive than 3 solar masses ignite helium before their contracting cores and become degenerate. Whether a star experiences a helium flash or not, the ignition of helium in the core changes the structure of that star. The star now makes energy both in its helium fusion core and in its hydrogen fusion shell. The energy flowing outward from the core can help the construction of the core, and the distended envelope of the star contract and growth. Secondly, the point that represents the star in the HR diagram moves downward, and to the left toward the hot star side of the diagram. Okay? And moreover, a few of the oxygen nuclei can absorb helium nuclei and form neon and then magnesium. Some of these reactions release neutrons, which have no charge and are more easily absorbed by nuclei to gradually build the even heavier nuclei. And these reactions are not important as energy producers, but they are slow cooker processes that form small traces of heavier elements right up to bismuth. You know that element? nearly 4 times heavier than iron. And many of the atoms in your body were produced this way. As the helium fuel is used up, the accumulation of carbon and oxygen atoms creates an inert core to cool the fuel. Once again, the core contracts and heats up, and soon a helium fusion shell ignites below the hydrogen fusion shell. And now that the star makes energy in two fusion cells, and it quickly expands, and its surface cools once again. The point that represents the star in the HR diagram moves back to the right, completed a loop. How do you see? What happens to a star after helium fusion depends on its mass. But no matter what tricks the star plays to delay the end, it cannot even survive long. It must eventually collapse, and its career as a star. The remainder of this module will trace the details of this process of stellar death. But before you begin that story, you must ask the most important question inside. What is the evidence for what you have learned for stars so far? Or what evidence shows that stars actually evolve as theories predict? You will find the answers in clusters of stars. Just as Sherlock Holmes studies specular dust on a lampshade as evidence that will solve a mystery, astronomers look at star cluster and say, aha, a photo of a star cluster freezes a moment in the evolution of the cluster and makes the evolution of the star being visible to human observation. Because they form nearly simultaneously from the same gas cloud, the stars in a cluster have about the same age and composition. And so, any differences you see among them are due to their difference in mass. That means that when you look at a cluster, you can see the effect of stellar evolution as it acts on otherwise similar stars on different. That is the cluster HR diagram and allows you to notice 3 important points and 4, exactly 4 new tabs. First, there are 2 kinds of stars clusters, open clusters and globular clusters. They look different, but they are similar in the way their stars evolve. You will learn even more about the clusters in a later module. You can estimate the age of a star cluster by observing the turn-off point in the distribution of the points that represented stars in the HR diagram. And 3, finally, the shape of a star cluster HIR diagram is governed by the evolutionary path the star takes. So the HR diagrams of all the clusters are especially clear in outlining how stars evolve away from the main sequence to the giant region. Then move left along the horizontal branch before evolving back into the giant region. By comparing clusters of different ages, you can visualize how stars evolve almost as if you were watching a film of a star cluster evolving over billions of years. If it were not for star clusters, astronomers would have little confidence in the theories of stellar evolution. Star clusters make evolution visible and assume astronomers that they really do understand how stars are born, live, and die, like humans or any other objects, not only planets in the universe. Now, let's became the scientific argument. Why is it only lower mass stars that outline the horizontal branch? This argument depends on timing. If a star cluster is young, it may contain a few massive stars, but because massive stars are so rare and envelop so rapidly, you are unlikely to see more than a few of these stars evolving through the giant or supergiant region of the HR diagram. Lower mass stars are very common and evolve slowly. So, in an older star cluster, you can see lots of stars in various stages of the post-main sequence evolution that outlines the horizontal branch. Now, contrast a different argument. What evidence can you cite those giant stars are main sequence stars that have expanded to large diameter? How do you see? I hope this is very interesting. Try to answer your answer, typing in the comment. Okay. Now let's start in our subtopics today's lecture: the death of lava main sequence stars. You know, contracting stars heat up by converting gravitational energy into thermal energy. Low mass stars have little gravitational energy. So when they contract, they don't get very hot, right? And this limits the fuel they can ignite. In the previous module, you saw those protostars less massive than 8% from solar mass and cannot get hot enough to ignite hydrogen. And this section will concentrate on stars more massive than 8% solar mass, but no more than a few times the mass of our sun. Structural differences divide the lower main sequence stars into two subgroups: very low mass, red dwarf, and medium mass stars such as the sun. The critical difference between the two groups is the extent of interior convection. If the star is convecting, fuel is constantly mixed, and its resulting evolution is drastically altered. And stars between 8% and about 40% of solar mass, the red dwarf, and have two advantages over more massive stars. First, they have very small masses, and that means they have very little weight to support. Their pressure temperature thermostats are set low, and they consume their hydrogen fuel very, very slowly. The discussion of the life expectancies of stars in the previous module concluded that the red dwarf should live very long life. The red dwarf have a second advantage in that they are totally convex. That is, they are steered by circulating current of hot gas rising from the interior and cool gas sinking inward. And this means that stars are mixed like a pot of soup that is constantly stirred as it cooks. Hydrogen is consumed uniformly throughout the star, which means the star is not limited to the fuel in its core. It can be used all of its hydrogen to prolong its life on the main sequence. Because a red dwarf is mixed by convection, and so it cannot develop an inner helium core surrounded by unprocessed hydrogen. And this is why it can never ignite a hydrogen shell and cannot become a giant star. What astronomers know about stellar evolution that indicate that these red dwarfs should use up nearly all of their hydrogen and live very long lives on the lower main sequence, surviving for 100 billion years or even more. Of course, astronomers can't test this part of their theory because the universe is only less than 14 billion years old. And so not a single red dwarf has died of old age anywhere in the universe. Every red dwarf that has even been born is still shining today. Stars like the sun eventually become hot enough to ignite helium as they pass through their giant phase. But if they contain less than 4 solar masses, they do not get to hot enough to ignite carbon. And the next fuel after the helium. Okay? And when they reach that impasse, they collapse and become white dwarfs. There are two keys of the evolution of these sun-like stars: the lack of complete mixing and mass loss. The interiors of medium mass stars are not completely mixed. Let's look at this slide. Stars of 110% solar masses or less have no convection near their center, so they are not mixed at all. Stars with a mass greater than 110% of solar mass have small zones of convection at their center. But this mix is no more than about 12% of the star mass. Medium mass stars, whether they have convective cores or not, are not thoroughly mixed. And the helium ash accumulates in an inert helium core surrounded by unprocessed hydrogen. Recall from earlier in this module that when this core contracts, the unprocessed hydrogen ignites in a shell and swells the star into the giant. In the giant stage, the core of the star contracts and the envelope expands. The star uses helium first in its core and then in an expanding shell surrounding a core of carbon and oxygen. This core contracts and grows hotter, but because the star has too large of mass, the core cannot get hot enough to ignite carbon fusion. The carbon-oxygen core is dead, and for these medium mass stars. All of this discussion is based on the theoretical models of stars and the general understanding of how stars evolve. Does it really happen? Astronomers need observational evidence to confirm their theory. And the gas that is expelled from their giant star gives visible evidence that some sunlight stars do indeed die in this way. Next topic, planetary nebulae. When a medium mass star like the Sun becomes a distended giant, its atmosphere cools. As it cools, it becomes opaque, and light has to push against it to escape. At the same time, the fusion shells become so thin and they are unstable and begin to flare, which also pushes the atmosphere out because of this outward pressure. And again, an aging giant can expel its outer atmosphere in repeated surges to form one of the most interesting objects in astronomy, a planetary nebula. So called because through a small telescope, it looks like the greenish blue disk of a planet like Uranus or Neptune. In fact, a planetary nebula has nothing to do with a planet. Okay, I hope you remember. And it is composed of ionized gas expelled by a tiny star. Study the formation of planetary nebula and notice 4 things. And first, you can understand what planetary nebula are like by using simple observational principles such as Kirchhoff's law and the Doppler effect. Second, notice that the model that astronomers have developed to explain planetary nebula, the real nebula, are more complex than the simple model of a slow thing and a fast thing, but the model provides a way to organize the observed phenomenon. Third, oppositely direct jets, much like bipolar clouds from protostars, produce many of the asymmetries seen in planetary nebulae. And fourth, the star itself must finally contract into a white dwarf. Most astronomy books say that the Sun will form a planetary nebula, but that may not happen. To ionize the gas and light up a planetary nebula, a star must become a white dwarf with a temperature of at least 25,000 Kelvin. Mathematical models show that a collapsing star of less than 55% solar mass takes as long as 1,000,000 years to heat up enough to ionize its nebula. And by the time the expelled gases are long gone. Models of the Sun are not precise enough to indicate how much mass will be left once it ejects its outer layer. If it is left with too little mass, it may heat too slowly. Also, some research suggests that a stellar needs a binary companion to speed up its spin and make it eject a planetary nebula. The Sun, of course, has no binary companion. This is an area of active research, and there are no firm conclusions. Are you disappointed that the Sun may not light up its own planetary nebula? At least that potential embarrassment lies a few billion years in the medium mass stars die by ejecting gas into space and contracting into white dwarfs. You have found evidence regarding the disk of medium mass stars in observations of planetary nebulae. Now you can turn your attention to the evidence revealed by white dwarfs themselves. So let's study more detailed white dwarfs. When you surveyed the star, you discovered that the white dwarfs are the second most common kind of star. Only red dwarfs are more abundant. Now you can recognize the billions of white dwarfs in our galaxy as the remains of medium mass stars. The first white dwarf discovered was the faint companion to favorite star Sirius. In that visual binary system, the bright star is Sirius A. The white dwarf, Sirius B, is 10,000 times fainter than Sirius A. The orbital motions of the star, shown in this graph, reveal that the white dwarf contains 98% solar mass, and its blue-white color tells that its surface is hot, about 45,000 Kelvin. Because it is both very hot and very low luminosity, it must have a small surface area. In fact, it is about the size of Earth. Dividing its mass by its volume reveals that it is very dense, about 2 times 10 in power 6 grams per cubic centimeter. On Earth, a teaspoon full of Sirius B material would be weighed, how do you think? More than 11 tons. A normal star is supported by energy flowing outward from its core. But a white dwarf cannot generate energy by nuclear fusion. It has exhausted its hydrogen and helium fuel and converted them into carbon and oxygen. When a star collapses into a white dwarf, it converts gravitational energy into thermal energy. Its interior becomes very hot, but it cannot get hot enough to fuse its carbon-oxygen interior. Instead, the star contracts until it becomes degenerate. Also, a tremendous amount of energy flows out of the hot interior. And it is not the energy flow that supports the star. The white dwarf is supported against its own gravity by the pressure of which degenerate electrons. The interior of a white dwarf is mostly carbon and oxygen nuclei immersed in a whirling storm of degenerate electrons. Theory predicts that as the star cools, these particles will lock together to form a crystal light. So there may be some truth in thinking of the interior of aging white dwarf as gray crystal of carbon and oxygen. Near the surface, where the pressure is lower, a layer of ionized gas make up a hot atmosphere. 850-pound human would weigh 50 million pounds of the surface of white dwarf. Or if we are speaking about our metric system, it means If you're weighing 150 kilos, massive bull, so you will be weighted mm, up to 50 million kilos on the surface of that white dwarf. And that strong gravity pulls the atmosphere down into a shell of yellow layers. If Earth's atmosphere were equally shallow, people on the top floor of skyscraper would have to wear spacesuits. And clearly, a white dwarf is not a true star. It generates no nuclear energy. It's almost totally degenerate. And except for a thin layer at its surface, contains no gas. But instead of calling a white dwarf as a star, you can call it a compact object. The next lecture discusses two other compact objects, neutron stars and black holes. The white dwarf future is bleak. As it radiates energy into space, its temperature gradually falls, but it cannot shrink any smaller because its degenerate electrons resist getting closer together. Degenerate matter is a very good thermal conductor. So as heat flows to the surface and escapes into space, the white dwarf gets fainter and moving downward and to the right in the HR type. Because a white dwarf contains a tremendous amount of heat, it needs billions of years to radiate that heat through its small surface area. Eventually, such objects may become cold and dark, so-called black dwarfs. Our galaxy is not old enough to contain, namely, black dwarfs. The coolest white dwarfs in our galaxy are about the temperature of the sun. Perhaps the most interesting things astronomers have learned about white dwarfs has come from mathematical models. The equations predict that if you added mass to a white dwarf, its radius would shrink because added mass would increase its gravity and squeeze it tighter. If you added enough to raise its total mass about 140 solar masses, the equations predict that its radius would shrink to zero. So please look into this point. This is called the Chandrasekhar limit after Subrahmanyan Chandrasekhar, the Indian astronomer who discovered it. It seems to imply that a star more massive than 140% solar masses would be not become a white dwarf unless it shed mass in some way. Stars do lose mass. Observations provide clear evidence that young stars have strong stellar beams, and aging giants and supergiants also lose masses rapidly. You may ensure this from this slide. This suggests that stars more massive than the Chandrasekhar limit and can eventually die as white dwarfs if they reduce their mass. Theoretical models show that stars that begin life with as much as 8 solar masses should lose mass fast enough to reduce their mass below 140% solar masses and eventually collapse to its form white. This mass loss a wide range of medium mass stars can eventually die as white dwarfs. I think it's enough for today. Next time we will be continuing our lecture. For this moment, do you have any questions or propositions? You may leave it in comments. And for now, I hope you enjoyed this lecture. And as usual, I am looking forward to seeing you next time. Bye.